Hey everybody, this is Professor Ross. Welcome back. In this video, we're going to be talking about errors and significance. So, two really key ideas that actually um, have made a lot of news lately in some ways, talking about significance levels and what they mean in statistics. And also, I believe are really, really vital for us to understand and think about when we talk about statistical errors and the possibilities of statistical errors and the limitations that we face when we do hypothesis testing. It's really vital that we understand those kinds of issues so that we can be well versed and intelligent users of things like statistical testing. So let's get into some notes here. Go ahead and do this. All right. So we want to talk about errors and significance. And one of our key learning objectives in this unit is to recognize potential biases in sampling, including surveys. Just a note on that before we dive into these things. If you've done a poor job doing a sample, getting a sample, and you have bias in your sampling procedure, the data you have will not be worth anything. So, the kinds of things we'll talk about today won't be very meaningful if we have lousy data to start with. So, it's always important to remember that we want to try to have good random procedures when we're gathering data in order to get into some of these further details. First, let's talk about significance and what we call the significance level. We've judged the strength of evidence against the null by examining p values in standardized statistics. If those p-values and standardized statistics suggest that we have moderate strength of evidence against the null hypothesis, what should we conclude? I mean, it's fairly clear if we have little or no evidence against the null hypothesis, okay, we'll stick with the null hypothesis. Or if we have strong or very strong evidence against the null hypothesis, okay, let's reject the null hypothesis and go with the alternate hypothesis. But what if it's moderate? Is that strong enough for us to reject the null? Or do we need to stick with the null? So this idea that there might be some kind of gray area can be challenging. And one solution is to decide before you do your hypothesis test, decide what you want to set as a cutoff. Am I going to require myself to just have moderate evidence against the null to reject it, or am I going to decide I want to make sure I have at least strong evidence before I reject it? Or maybe I decide I want very strong evidence against the null before I reject it. Deciding this level ahead of time is what's called setting a significance level. It's a value used as a criterion for deciding how small your p value needs to be in order to have strong enough evidence to reject the null hypothesis. We often symbolize it with another Greek letter. That's the Greek letter A, called alpha. And so we often set an alpha ahead of time. For example, we may say alpha is 0.05. And just tell you right now, that's the most common significance level that's used, alpha as 0.05. In fact, it's often assumed to be the default significance level if the person talking about the statistics or research doesn't say anything else. Everybody just kind of assumes the significance level is alpha of 0.05. But it's actually really good to be explicit about it and to say what your alpha is. Once again, it should be set prior to obtaining the p-value. If you check your p-value and then you're like, oh, maybe I'll set alpha, just here so my p-value is just strong enough to reject the null. That's kind of cheating in some sense, and it's not good practice. So we want to set it before we do any studying of our data, looking at the data, calculating p-values, any of that stuff. So what does this mean if we set alpha, the significance level, to 0.05? I've got our little table of p-values here, and what we're saying is we want p-values below 0.05 in order to feel like we're going to reject the null hypothesis. Let's take a look. This is p-values above 10%, between 5 and 10%, so those would still be above. If we set alpha at 0.05, it basically cuts through here. and says if you're below here, this is where you would reject your null hypothesis. And if you have anything above here, that's where you would retain the null hypothesis. And so we'd be saying, okay, not much evidence or moderate evidence is not strong enough for us to reject it. We're going to stick with the null. On the other hand, if we get down here where we have strong evidence or very strong evidence, that's going to be strong enough for us to reject the null hypothesis. And so that's what's most typically the case. Just so you know, there are some research settings where researchers decide to use other significance levels, like maybe 10%. And they say even moderate evidence is going to be enough for us to reject the null. Or they might be down at 1% and say, look, we're going to stick with the null unless we get very strong evidence. So that's what the significance level is all about. We'll most typically use an alpha of 0.05. If you know it's ever not indicated, you can assume that's it. But watch and remember what that's telling us. It's telling us how strong our evidence needs to be. On to our other major topic for the video, which is errors in tests of significance. Now, errors is another one of these words that gets used in a kind of every day-to-day context, but we mean something very specific by it in statistics. So what we don't mean is the day-to-day meaning of mistakes. We're not talking about statisticians clicking on the wrong button on the applet or, forgetting to add a number into their data set or asking the question the wrong way on the survey. We're not talking about those kinds of errors. What we are talking about is when our hypothesis test comes to the wrong conclusion and we don't necessarily even know that it has happened. And it comes to the wrong conclusion because all of our procedures are based on probabilities. So let's take a look at an example to see what we're talking about. In the past, we talked about researchers trying to see if they could predict the winner of Senate races. So they predicted 23 of 32 Senate races correctly based on how people judge the facial pictures of the people running in the races. So 23 of 32 turned out to be pretty different than what we might expect by chance alone. By chance alone, we'd expect results like this, more around 15, 12, 15, 18, even up to 21 would be pretty common kinds of results. 23 ended up being way out here, and the p-values suggest that it's about 1%. Only about 1 in every 100 times might we see a result like this by chance alone. So we say, okay, that's a very low p-value, very strong evidence, right on that borderline of strong to very strong evidence against the null hypothesis. Let's reject the claim that it's by chance alone. However, there is this 1 in 100 times where we would expect to see this by chance alone. And maybe, just maybe in this study, it happened to be that 1 out of the 100 times where this result did just happen to happen by chance alone. That's what we mean by an error. It means we do everything right. We come to this conclusion. We say low p-value, strong evidence against the null, reject the null hypothesis. But in reality, what actually happened was that just one rare chance, and we really shouldn't have rejected the null hypothesis. Now, I mentioned without necessarily even knowing it, the researchers who did this study don't have any way of knowing what that they, whether that error has occurred or not, because they don't have data for the entire population. So we do the best we can, and we come to the conclusions that we believe to be true. But it's always good to acknowledge the possibility of this error happening. Now, there's actually two types of errors, so we need to identify the two kinds of ways we can go wrong here, and with the two types of errors that we should acknowledge when we're doing tests of significance. These are just kind of arbitrarily named, type 1 and type 2, so it'll be up to you to memorize those two names, but I'll try to give you some description and help them kind of stick out in your mind. A type 1 error is sometimes called a false alarm. That means we've kind of decided, hey, there's something to see here when there really wasn't. This is when the null hypothesis is actually true. This kind of chance alone or already accepted claim, that's actually the truth. But our test results indicate we should reject the null hypothesis. That's just what we were talking about on the previous slide. So that's why it's called a false alarm, because we're kind of like, hey, it's not the status quo. It's something new that we're seeing here, when actually that's not really the case. What are the chances of a false alarm happening? Well, we can't ever know for sure that a false alarm did happen, but we can specify the chance of it happening, and it's related to significance level. There is an alpha percent chance of making this error if the null hypothesis is true. So alpha is typically set at alpha, we just said the default is 0.05 or 5%. So when we reject a null hypothesis, there's typically a 5% chance that we have a false alarm happening here. Why is it 5%? Well, if you think back to like this diagram here, if we set alpha at 5%, we basically say, hey, if results happen out here, then we're going to reject the null hypothesis. But 5% of the results happen out there, which means 5% of the time we'd have a false alarm. So it's directly connected to alpha. This is a reason why we like to pick an alpha around 5%. Usually folks are fairly comfortable with a 5% chance of an error. If you push it down to 1%, you'd have even less chance of an error, which is good. But you'd also have to have even stronger evidence against the null. So there's kind of this balance of where do you put alpha? If you say, well, why don't we raise alpha up to 10% so that we don't have to have as strong evidence? Well, if you raise it up to 10%, then you got double the chance of a type 1 error. So it's this kind of balance game, and a lot of statisticians and researchers feel pretty comfortable at the 5% level as the balance. So that's a type 1 error. That's when our test says reject the null hypothesis. When our test says retain the null hypothesis, don't reject it, then we may be facing a type 2 error, a missed opportunity. We could have found something going on here, but we missed that chance. That's when the null hypothesis is actually false, but our test result indicate we should not reject it. So we get a higher p-value. We say, oh look, not strong evidence against the null, let's not reject it. Then there's a chance we have a type 2 error. Now, how do we can't ever know for sure if we had a type 2 error, but we can talk about the chances of it. It's a little more complicated. It's not just related directly to a single number, but it is connected to the idea of what we call power. So the power of a test is 100% minus the chance of a type 2 error. Another way to think about that is the power and the chance of a type 2 error add up to 100%. What is the power of a test? The power is the chance of making the correct conclusion when the null hypothesis is false. That is, the power is the chance of rejecting the null hypothesis when it's actually false. So power is the good thing. If the null hypothesis is false, we want to reject it. Type 2 missed opportunity is the bad thing. The null hypothesis is false, but we failed to reject it. So those two things are kind of two sides of the coin. And whatever there is for power, then the rest is type 2 or vice versa. You can do things to analyze the power of a test. We're not going to get into that in this course, but I will, if I'm expecting you to talk about type 2 error, I'll always give you the power. Like I might say, we ran this test and we had a power of 70%. Then you should know that that means that the chance of a type 2 error is 30% because they add up to 100. That's not great. 30% is a pretty big chance of a type 2 error, a missed opportunity. So ideally, we would want to test with high power, let's say like 90%, and then that would reduce our type 2 to 10% or even higher, 95%, and reduce type 2 to 5%, that kind of thing. Um, how do you get higher powered tests? One of the main ways is to have bigger samples. So the bigger your samples, the more powerful your test, the lower your chance of a type 2 error. One of the key ideas to take away from all of this is that we can lower our chance of type 1 error by lowering alpha, but that actually results in a less powerful test. So besides sample size, your alpha is connected to your power, and a lower alpha means lower power, which means a higher type 2 error. So they're all interconnected. The keys for you to know: type 1 is a false alarm, and there's an alpha percent chance of making that error if the null is actually true. Type 2, missed opportunity, 100% minus the power. Alrighty, here's a little table that kind of summarizes those two types. And I like to use this table kind of working from left to right. So if I'm trying to figure out what error I might be looking at in my test, I look at, well, what was my decision for my test? Did I reject the null hypothesis? Then I might be facing a type 1 error. Did I not reject the null hypothesis? Then I might be facing a type 2 error. When is it an error? It's an error when our conclusion actually does the opposite of what's really true. So if I rejected the null, but the null is true, then it's an error. If I rejected the null and the null was false, I did the correct decision. That's called the power of the test. If I didn't reject the null was true. That's a correct decision. And that's just kind of the boring thing. Null was true, didn't reject it. Okay. If I didn't reject the null, but it was false, that's a type 2 error. So that table can help some folks think about which errors. So, all right. So that's errors and significance levels.